So the arc length, basically, the concept, just to quickly remind you, is any curve in space from any point A to B, we are able to calculate the arc length of such a curve. Now we've seen already the arc length idea. You would have seen an idea earlier, which is of a parametrized curve, in fact. And parametrized curve have arc lengths which are calculated using, for instance, if in 3 dimensions, the parametrization x equals ft, y equals g of t, and z equals h of t, for instance, was a parametrization of some curve in 3 dimensions. Then basically the formula, the length L of the curve represented by this parametrization from A to B, which is, of course, we're interested in calculating the length from A to B of this particular strip, or I'm sorry, this curve, then it is by definition, in fact, df dt squared. It's the square of each of the derivatives with respect to t. So we do this, and then we of course integrate this overall with respect to t. Now this is something you would have seen before in earlier calculus courses, like for instance in calculus 2 you would have met this. In any case, I won't go into details of how this is derived, but this is the arc length of a curve that is parametrized by in 3D as given here. Now we can use the same idea, because if you think about it, any vector function is in fact has these 3 components, which we've seen before. It is the same as parametrizing curve. So RT is parametrized this way. Now if you look at it, this means essentially what we're saying is that L can in fact be written as, from A to B, the magnitude of R prime of t. Because if you think about it, what is, if you see here, this implies that R prime of t is in fact f dash, g dash, and of course h dash, in short, without just dropping those t's. So if I were to look at the magnitude of that, okay, the magnitude of that would in fact be square root of f dash squared plus g dash squared plus h dash squared, which is the same as that's why we have this here. If you look, that is the same as you see here in this formula. So we end up with this result, which is the length of a curve, or length of the path of an object represented by the vector function r of t. Let's look at, as an example, let's look at the helix again, cos t sin t, and let's say we are looking at the curve from the point 1, 0, 0 to let's say 1, 0, 2 pi. So this would first, one of the things you need to do in this case is figure out what is the range of values of t. Well, clearly t is going from 0 to 2 pi. In general, in this particular case, it's quite obvious because of the presence of this component direct, which is just t itself. So if you look at this number here, 2 pi, and this number here, they both represent, of course, t. So t is equal to 0. Now, of course, cos of 0 is 1 and sine of 0 is 0. And similarly, cos 2 pi is 1 and sine 2 pi is 0. Okay, so that's fair enough. And they have to work out that way. But it's very obvious that what the values of t are. In case it is not obvious what the values of t are, or this range here is not given, what you can do is actually equate each of these. For instance, you can say cosine t equals 1. What value of t will satisfy that, simultaneously satisfying sine of t equal to 0 and t equal to 2 pi. So then what we need to do first, once we know the values of t, the next thing we can quite easily do is calculate the derivative here, which is minus sine t, cos t, and 1. Calculate the magnitude of this, and that turns out to be square root of sine squared t plus cos squared t plus 1 squared, which is 1, which is equal to sine squared plus cos squared, as you know, is 1. So that gives us square root 2. Now we proceed to the integration from 0 to 2 pi of square root 2, which is the magnitude of the tangent vector, dt, and that's then equal to simply put square root 2t from 0 to 2 pi, which turns out to be just 2 square root 2 pi. And that's the arc length of this curve. Now we look at something called the arc length function. In fact, the arc length function. The arc length function is basically defined by the letter s of t, and it is equal to the integral from 0 to t of the magnitude of the tangent vector du. Now u here is a integration variable. What you will notice here, sorry, this is not a0, this is a. So from some starting point a to some point t. So basically what we're saying is if we have some curve and this is a starting point, then the other point is open. So in other words, the curve is, you can just name a point, and the formula that we get from this will give us a point and will tell you what the length of it is. So what, for instance, so if you were to calculate in this example that we have here, that we've just done above, what would happen is it would simply be the for the helix from 0 to 2 pi, instead of from 0 to 2 pi now, we'd be looking at the of exactly the same thing, which is square root 2 du, which turns out to be, the result is root 2t. So we end up with root 2t. Now, going back to the example we had, when t was 2 pi, you simply would be substituting, instead of t, the 2 pi, and it would give you the answer. But you could also substitute 3 pi, or 4, or 5, or 6 pi, or 7, or any number, and it would quickly give you starting point 0 up to whatever point you want. So that's one of its advantages. The other advantage of this arc length function, in fact, is that it can help us to reparametrize. So it can help us to reparametrize, for instance, using the parametrization t is s over root 2. Now, using this parametrization, in fact, we would, our original function r, or function of t, becomes now a function of s. And we do this as follows. Let me just show you. Okay, there. Okay, actually, I can't see it, but let me just move this up. Sorry. So, what we're saying is just to remind you, we had r of t was cos t, sine t, and t. So now, under this reparametrization, r of s as a function of arc length is in fact cosine of s over root 2, sine of s over root 2, and s over root 2. So this would be the reparametrization in terms of the arc length, the vector function r. Okay, so this is simply one of the benefits of having the arc length function, is that we can reparametrize the vector function in terms of the arc length. So we're going to stop here.